Hi guys, do you need me to go over drag again? I posted the software. So I called it ISS with drag, but really I was simulating a small satellite. So if you go into the equations of motion function, you can change the mass and the surface to make it the ISS if you want. I don't know why. I just left that name because it was code from your second homework, basically. That was running the ISS, but the drag was for a CubeSat. Anyways, any questions on that? Play with it. Change mass, surface. Okay. Gravitational perturbations. Okay, let's do this J2 once and for all. Let's prove that the equations I gave you quite some time ago are actually valid when you want to take into account oblateness at the poles. So we remember for a sphere of uniform mass distribution, remember this was the potential, specific potential energy, right? And from this, you can derive the acceleration by operating the gradient of on that function, which is equivalent to doing this, the partial of v with respect to x in the I direction or x direction, partial of v with respect to I in the j direction, partial of v with respect to z in the z direction, right? These are all minuses, of course. So obviously this is a function. You want to have it somehow as a function of Cartesian coordinates so that you can take those partials, right? And that's easy to do if r is in Cartesian coordinates. You know, if the vector r is expressed like this, we've done this. You can prove to yourself that operating on this function, the following, you get eventually what we've been using. This is r cubed, r vector, okay? Now, what if the planet is not a sphere anymore, but it's an ellipsoid, and I'm exaggerating, of course, here, where you just squeeze at the two poles, north and south, the circle that is the equatorial circle remains a circle, so it's just squeezing there at the two sides. So we're still in ECI, but the shape now has changed. This is my x direction in ECI, this is my y direction in ECI, and this is my z direction in ECI. How do I compute the acceleration that at a certain position r, my spacecraft experience, so this is my vector r, as usual. Well, we'll have to do something to this potential here. And that's usually what is done, is the Keplerian part plus something else. Let's call it capital phi. That's how your book calls it, I believe. So there's something else that we need to add so that when we take the gradient of this term here, the gradient of this phi minus the gradient of this is going to give me some kind of perturbation acceleration that I'm going to call the perturbation due to J2, and it will be clear today why that's called J2. Is just the letter for some constants in a series expansion. So now, if this is an ellipsoid, as I said, that it's circular, so it's symmetric about the z-axis, and if instead of using Cartesian coordinates, I use right ascension, let's call this theta, some kind of declination from the z direction that I call phi, and then r, spherical coordinates, basically. What depth phi will depend on these quantities here. On which ones do you think it should depend? if the body is symmetric about the z-axis. So what I'm trying to take into account at the end of the day is the fact that when I go north on my orbit or south, I'm going to see less mass, if you want. I see the bulge at the equator. I see more mass there. Do you think this function, whatever it is, should depend on theta? Is it going to make a difference? If I take this vector r, whatever it is, and I just rotate it about the z-axis at the same angle phi without changing its magnitude, it's not going to change what it sees because of the symmetry. So theta is not going to be there, right? So I have here some kind of additional potential that is function of phi, little phi, and r only. Okay. And I eventually will give it to you, like in the next step, and we'll have to take its partials with respect to x, y, and z. Because again, if I'm able to take the partial of this, I'm going to be able to add here, I'm going to have minus mu over r cubed, r, that's what we had before, plus that perturbation. That's what I want to compute. And you have it in your code. You've had it for a long time. It's that additional piece in the equations of motion. Okay. Now this function is given in the book, and it just comes from observations of satellites' motion. This is nothing that you can really derive. Is fitting constants according to observations. I'm just going to give it to you here. We'll make some comments. It's a series. K goes 2 to infinity. J of k, r over little r to the k, and then pk cosine of phi. Okay, what are these things? Well, this is the mu of the planet Earth. This is the radius where you are. This is the radius where you are. Jk is called the zonal harmonics, or harmonic, one of them. These are just a-dimensional constants. And this one comes from satellite observation. So basically people have been taking measurements of how satellites fly, especially in LEO. They define a function like this, a series, and they try to fit it to the data. That's nothing else. R is the equatorial radius, which is the typical value we've been using, 6,378 kilometers. And pk are Legendre polynomials. Which I'm going to write in a second. So this is, in general, taking into account more than one effect that is symmetric on the z-axis. So imagine that if you instead of having just a bulge at the equator, you have several bulges, but they're all symmetric. Does it make sense? So you have a planet which, instead of being a sphere, is a series of little cylinders on top of each other. So the bulge is not just one at the equator. You have several, of these, keeping symmetry about the z-axis. So you can imagine all sorts of shapes with symmetry about the z-axis, right? Make sense? You have a bulge at 0 latitude, then instead of going like an ellipsoid to the North Pole, you have, you decrease the radius, and then you have another bulge, and then you may have another one, etc., etc. So you're trying to model all these irregular shapes, still with symmetry about the z-axis, with something like this. So you have an infinite series where each one of these constants is representing one of those bulges, pretty much. And again, the numbers that correspond to these j's are given by satellite observations. The j2, which is the most important one. So j, you start from 0 here. No, you start from 2, because that's the first one that really matters. j2 is a constant that is in your code. I don't have it on top of my mind, to be honest. I didn't write it down. I don't memorize it. But it really dominates all the zonal harmonics. So that is really the one that we care about, the very first constant. The other ones are there, but they have, everything okay? Wow. Everything else is a lot less. The pk is one thing that I want to write just to be thorough here. Pk of a independent variable x will be 1 over 2 to the kth power factorial of k d with respect to dxk of x squared minus 1 to the k power. And if you really stop at k equal 2, so you only take the first of this series at the end of the day. So basically, if I take these, combine them together, k is equal to 2 and nothing else, I get the function that I care about, which is this. Say 2 over 2, mu over r, big R over little r squared, and then I have 3 cosine squared of phi minus 1. So as far as we are concerned, this is really the phi that I need to operate on. I'm going to take the gradient of that to add something to mu over r cubed r. Does all these make sense? So since we started flying satellites, people have been taking measurements, and again, they've been feeding this kind of function to the data to try to come up with something that mathematically we can handle, which is quite complicated, but it's basically a series expansion. We do that all the time. Fourier series would be an alternative to doing this, where you try to represent an unknown signal for which you have data, and you try to fit the constants until you more or less following that data. That's what's happening here. Except it's done in some kind of intelligent way, because if you're trying to model only effects due to the fact that there is symmetry about the z-axis, but now the planet is some kind of collection of bulges, then of course you don't want to include the theta in the independent variables for capital phi, of course, right? Okay, any questions on this? This is all information that we are given. By the way, just something that we're not going to see, but there is more to that. Our planet doesn't really have only symmetric shapes that are symmetric with respect to the z-axis, okay? There's also bulges that have no symmetry with respect to the z-axis. You have mountains, you have oceans and other weird shapes that pop up, and so those are called zonal harmonics. Then we talk about I don't think I'm going to need this, so I'm going to write it here. So there are other functions that you can define, but basically the ones that we call zonal harmonics are perturbations that are symmetry about z, right? And that's what we're doing. We're just doing the first one. Then we say we have sectorial harmonics. They take into account longitudinal variations. For example, if you imagine to look at the planet from the North Pole, so now this is north coming at us, you will take into account the fact that, I don't know, in this range of longitudes, there is a bulge here. There is more mass. There is a mountain there. There is Everest. I don't know, something like that. So there are other series expansions and constants that are called sectorial harmonics that take into account perturbations due to the fact that in certain longitude areas you have deformations with respect to being a sphere, more or less mass in a certain range of longitudes. And then there is even more. There are the tesseract harmonics. These are really localized. You can think of these as you focus on a certain region longitude-wise and latitude-wise. So if this is your ideal planet. Now, maybe here around Mountain Everest, there is something going on where there is more mass. So it's really focused on certain specific regions of the planet. So as you add all these together, and I think SDK has the capability of selecting J2, as you're doing for homework 2, for example, and more, the additional perturbations that you have into this potential and then eventually into the acceleration R double dot, well, you will have more terms. And it really depends on the problem you're trying to solve. If you're working in low Earth orbits, then you really care about these mostly. But as you go higher, for example, geostationary orbits, you may want to take into account something else because it does affect your motion. So it really depends on how long of an orbital propagation you're performing, how much time into the future you're looking at, and your altitude at the end. But let's derive what we want to derive here. It's going to take a little bit of math to do that. Okay. Oh, one thing. Look at this expression here. Notice that this goes to 0 when the cosine of phi is obviously the square root of 1 over 3, which is about plus or minus 35 degrees. This is when you transition from adding more force to the standard one, to the standard acceleration, to actually having less, and vice versa. So, is that a problem? Do you see it? So the 35 degree, keep in mind that 35, the angle phi is the complementary of the latitude, okay? So you count in 35 from z. It's that angle plus minus where you're actually going through the bulge. That's what's happening. You're going from having less mass under you to having more mass as you enter the equatorial region. And then if you keep going, you go to minus 35, then you have the opposite. You don't see the bulge anymore, you go to less mass as you approach the pole. Make sense? All right, so having said that, I want to probably leave that sketch there. How do I do the, how do I compute the gradient? Well, there's one thing we need to keep in mind. First of all, from this figure here, using a simple triangle, you can derive the following. This is squared, and this is over z. We use that. So my perturbation J2 that I want to find has to be minus the gradient of phi, which is minus the partial of phi with respect to x, I minus the partial of phi with respect to z, j minus the partial of phi with respect to z, k. I do not have, in that phi expression, I don't have a direct dependency on x, y, and z, right? I can't just take the partials right away, but they're there. R is a function of x, y, and z, and phi is right here. It's an ugly function of x, y, and z, but it is a function of x, y, and z. So we'll just do the first one. The second, this one, d phi in dx, for example. The other ones just follow with the same procedure. Well, first of all, d phi, we notice this, d phi in d theta by construction is 0, obviously. And then, for example, d phi dx, how do you do this? Function of a function, right? My hands are freezing. I'm not kidding. How would you do that? Phi is a function, explicit function of r and phi, little phi. So I need to apply the chain rule, right? So I have to do partial of big phi with respect to, for example, r, and then the partial of r with respect to x, plus the partial of big phi with respect to the angle little phi, and then partial of the angle phi with respect to x. Make sense? So we just do it for the x, and then y and z is the same steps. It's a nice exercise. I don't think I want to erase that. Okay. Let's do, for example, d phi with respect to r. Remember, that's phi down there. If you do it in one step, you should get these. Mu over r squared, big R over r all squared, and then this part doesn't change. Agree? You take that function, you only look at the part that has an r, and that r is actually cubed at the denominator. That's why there is a -3 up here, and that's why there is an additional r at the denominator. End of the story. The rest is just the same. Make sense? So forget about 3 cosine squared minus 1. Forget about big R, which is a constant. Mu is a constant. J2 is a constant. Again, the value is in your code. The only thing that is changing for me right now is little r. And it's the partial of 1 over r cubed. That's what I'm taking. Yes?
So, should J2 be in?
Oh, yeah, J2. Yeah, thank you. Yeah, it's a constant. Okay. Let's do the partial of phi with respect to little phi. This is -3 J2 mu over r, big R, little r squared. And then you have sine of phi, cosine of phi. And let's verify that these make sense. Now phi is the variable I care about. I see a cosine squared, so the 2 goes down, the divide by 2 goes away. The 3 is here because there was a 3 there. The derivative of cosine is minus sine, minus is there, and cosine again. That makes sense? Agree? Now the ugly one is this one, partial of, what am I doing? Oh, yeah, the little phi with respect to x, for example. That's definitely the ugly one. Because phi is that function, so I have to take the partial with respect to x of the arctangent of x squared plus y squared over z. And of course we all remember what this is. What is the... I don't remember what it is. Do you remember what this is? I have it here. I'm cheating. It's 1 over 1 plus x squared, right? Anyways. So if you use that, you get xz over x squared plus y squared plus z squared, that is multiplying 1 over this. Okay? Yeah, I think we don't need this anymore. Not done. Which, I can continue down there actually. So this down here is r squared, right? So this is equal to, it's equal to xz over r squared, bless you, 1 over x squared plus y squared, which can be further manipulated to xz r cubed over 1 over x squared plus y squared that I am dividing by r, x, z, r cubed. Now this is, if you look again at that triangle there with r being the long side, you can show that this expression here is the sine of phi. So finally, what I really want to get at is that I get x z over r cubed sine of phi. Fine. Okay. So we need to put it all together. What is dr? I am missing one piece of all these partials. I've done d phi with respect to r. I've done this one. I have done this one. I haven't done this one. Now this should be the easy one. What is dr dx? It's x over r. R is this. So show it to yourself. Do the partial of this with respect to x. This square root goes to the denominator. Becomes dr down there, and then you left with 2x. The 2 simplifies. That's what you get. Okay, so we can put it all together. Let's see. So I'm putting together this with all the pieces that I have. Let's be careful. I have minus 3 over 2 j2 mu over r squared. Then I have big R, little r, all squared. I have 3 cosine squared of phi minus 1 that multiplies that x over r. And then I have minus 3 j2 mu over r, big R, little r, still squared, cosine phi, sine phi, and then that's why I wanted that sine phi to appear there, because here I have xz over r cubed, another sine of phi that simplifies with this one. Now I have a note here, double check, but I wrote down that the book actually has a typo at some point for this one. For this one here. So check the book. I think they have a typo. I don't remember what it is. I think they still have the divide by 2, which shouldn't be there. Anyways, the final expression they have is correct. All right. There is another tool that we're going to use. Cosine of phi is equal to z over r. Still looking at that triangle up there. So, if you substitute for cosine of phi with z over r, I'm trying to get the expressions that you have in MATLAB, basically. The relative acceleration with J2 formula that I've given should match this. Minus 1 that multiplies x over r minus 3 j2 mu over r squared, r, big R, little r squared, and then, well, this becomes another z over r, right? But then I have another z over r. So I moved an r here. Bottom line is this is z over r squared x over r. I know it's ugly. We're just doing it for x. So now this should look kind of similar, I think. This is in common. This is in common. This also, the z over r squared. There is an x over r. J2 is in both of them, of course. So if you do a common denominator, if you want to call it that way, you have minus 3 over 2 j2 mu over r squared, big R, little r squared, x over r, and what you're left with is 5 times the z over r squared minus 1, and that's the end of the story. So this was the partial of phi with respect to x. And let me just sit here for a second and verify that I didn't miss any components. No. So this is the first of those 3 expressions that you should have in your MATLAB code. I think it's actually expressed that way. Likewise, you have any questions? It's a lot of derivatives. There's really nothing else. Likewise, I think I can write it here. The other two that you should recognize in your MATLAB code will look like this. Z over R squared minus 1. So this is on the y direction, the partial with respect to y. The difference is this one, right here. The last one is slightly different. Is minus 3 over 2, J2, mu over R squared, big R, little r squared. There is a Z over R here, and in the parentheses I have still 5 Z over R squared, but then there is a minus 3. That's the difference. And the procedure to prove this is exactly the same. You have to do the partials. Yes?
Are those two supposed to be little phi or capital Phi?
Big phi. Thank you. Yep. Okay? So if you want to put it all together and make it look like the code you have, because I think it's a good thing to give closure to all this math, your perturbation due to J2 is you collect a few constants and you just have these terms here, x over r, 5z squared over r squared minus 1. This is in the I direction. Then you have y over r, 5z squared, r squared, minus 1 in the j direction. And finally, z over r, 5z squared over r squared minus 3 in the z direction. That is finally your J2 perturbation, the one that we've been naming so many times without demonstrating it. That's the demonstration. You start from a modified potential energy, and you know that there must be symmetry because that's the only thing you're modeling is zonal harmonics, nothing else. The first one is the most important. We stick with just the J2 one, and going through a few derivatives, you can get to this, which should correspond to what I gave you, the rel acceleration with J2. If it doesn't, let me know. It should. I think one suggestion I have for you, you can take it as an uncollected homework if you want, but you've been playing with this for a while at this point, is but you could do this as an additional work. There is the example 12.2 in your book that is a good example of J2 simulation to see the effect of J2. Now we do know, we have seen in the past that one of the effects of J2 is changing your RAN, right ascension of the ascending node, and that we can use that for creation of sun-synchronous orbits. But we're not there yet. We can't prove that yet because this is all Cartesian coordinates. I haven't talked about any orbital parameters, right? So, any questions about what we have done? Is this all clear? I needed to give you an explanation for that function that I gave you at the beginning of the semester, and this is the explanation. This is how you model your sphere and squeezing it at the poles. It's satellite data. The J's come from satellite data. One comment about last lecture, I think at some point I was just quickly saying, okay, once you start having orbital perturbations, your orbital parameters will not be constant anymore, right? Especially these first 5 here. And I wrote something without giving it a name. I said, okay, we'll see differential equations that will tell us how these orbital parameters change. GVE stands for Gauss variational equations. That's exactly what we'll do next time. They are equations that give you the rate of change of A, the rate of change of E, the rate of change of I, sorry for the 2 dots on top of each other here, the rate of change of omega, the rate of change of little omega, and the rate of change of theta, depending on the perturbation that you select to turn on or off. Drag, we'll analyze that. J2, because this is, again, this is all nice in Cartesian coordinates and it allows you to integrate the equations of motion in ECI with x, y, and z, but at the end of the day, you're not going to see how your orbit, as an orbit, really evolves if you look at Cartesian coordinates. Okay? I think that's all I wanted to really do today, but I am asking you guys if you have any questions, since you have an homework that is due soon as well. Yeah.
So is the J2 is the combination of the zonal, sectorial, and tesseract?
No, the J2 is only the first zonal harmonic. It's just the first one. So I should have brought something to explain, but again, imagine a ball and you squeeze the poles and nothing else happens, so you just get an ellipsoid that is symmetric about the axis on which you're pushing, right? But then, and that's what J2 is doing. It's representing that shape. But then you could have different shapes where the bulging is actually not regular. It changes with the latitude. And as you change the latitude, you will have to add more J's into that series expansion. And people do it. STK, when you select the HPOP, the high fidelity orbital propagator, that does include J up to, I don't know, J4. There's more. Long-term, effect of these perturbations, even if they are negligible with respect to J2 in principle, can be actually not negligible anymore. If you're propagating an orbit for months, then they're going to have an effect. So these are zonal, and then we said the sectorial ones will take into account if you are the z-axis and you go around on the longitude of the planet and you have more mass between 0 and 10, and then you have less mass between 10 and 20 degrees longitude, and so on and so forth. Those different concentrations of masses or bulges that you may have in the longitudinal direction, that would be another type of series expansion where now theta is a variable that you need to take into account. And so that's the next step of fidelity. And then sectorial ones are the ones, tesseract ones are the ones that will take into account actually specific locations. You can combine them all together. So high fidelity propagators, if you need high fidelity, they will combine all these different bulges symmetric to the z as a function of longitude, or even just localized, and they will take them into account. As I probably mentioned a couple times, Google the GRACE mission, G-R-A-C-E. I'm not sure it's still operational. They've been talking about a GRACE 2. It's a formation flying mission with 2 satellites flying in a leader-follower configuration with precise accelerometers to map the gravitational field of the planet. So what they measure with the accelerometers is turned into an actual shape of the planet. And if you go online and search for this mission and the websites that they've been maintaining, you can download updated J's. These constants can be downloaded. You can make better models in MATLAB if you want. And they also have 3D visualization of the shape of the planet according to the spacecraft data. And it really looks weird. There's nothing to do with a sphere. There are bulges all over the place, of course, as you can imagine. Mountains, oceans. Attraction from the moon changes a little bit mass distribution, as we know. Right? We have the tides. So, but this is definitely one of the most important ones that we need to handle. Any other questions? About the homework? Is it okay? Should be okay. So you have a test next week, right? Look at exam 2 from last year, please. Do it. If exam 1 required a couple of calculations, exam 2 last year required, I think, 0 calculations, probably. It's all based on visualization in 3D of orbits, orbital parameters, what we've done. There was the very first question I still remember is if I give you an orbit of an inclination of 50 degrees, what is the maximum latitude you're going to see? What is that? 50. So the exam 2 goals for last year, and it should be the same for this year, is that you're just aware of these orbital parameters and what they mean, and maybe sketching something on a piece of paper, you can visualize what I'm asking you. So if, you know, this is ECI, and your plane of the orbit is at 50 degrees, can you ever see a latitude that is above 50 degrees? I'm not going to solve it for you, but there's zero calculations you have to do. Really. What else did I ask last year? I'm trying to remember. Well, there were a couple of questions about the other angles. But there was no calculation really that you need to go through. For example, for a sequence 3, 2, 1, if the second angle is 90 degrees, what happens? It's a singularity, right? So maybe I said in a sequence 3, 2, 1, the three angles are something like 10 degrees, then the second one is 90 degrees, and then again 10 degrees, and I asked the question, what's going on here? This was compared with another one, I think, 20. Again, I don't remember exactly the numbers. The second one was 90 degrees, but basically there is no difference between these two rotations if you do a 3 to 1 and you go through a singularity, because the first rotation cancels out with the other one. Think about it, but yeah. There was, most of the questions, actually all the questions, I think they required really zero calculation. In fact, there was one question, I think number 2 or 3, where I asked, I think I gave Cartesian coordinates, position and velocity, and I asked, convert these into orbital parameters by just drawing a sketch and not doing any calculations. And then I said, if you do it without calculations, by showing me with a sketch in 3D that you can figure them out, you get full points. If you actually do the calculations, you get less points. Because the point was, I don't need you to go through the pain. I just want you to show me that you understand what these orbital parameters are. Now, I don't remember the numbers, but it was something along these lines. Say that I'm giving you in X, Y, and Z. I'm just making this up. Your position is this vector, right? At time 0. So position at time 0, say that is, I don't know, 10,000 kilometers on the X, and 0, 0 on the other two, right? So you're here, and I don't know, say that your velocity is going that way. So if this is X, this is Y, and this is Z, I believe I gave something along these lines. The velocity is now 0, square root of mu over R0, 0. Something like that. Which means that the velocity now is a vector, so this is your position at time 0, right? And this is your velocity at time 0. They are at 90 degrees, first of all. It's purely pointing in the y direction. So what do you think the orbital parameters for this orbit are? Without calculation, just thinking. I mean, you can write sentences, of course, but without having to do really any calculations almost. So first of all, let's start with the, I don't know. You can start from anywhere here. What is the inclination of this orbit? 0. Because if it's a Keplerian, of course, and that's what I was saying, you know, no perturbations. If it's a Keplerian orbit, the cross product of R and V is the z-axis, basically. And that's not going to change. And if you are with the z-axis with H, you're 0 inclination. End of the story. Look at this. This is the velocity of what kind of orbit? All right, E is 0. That's enough. Look at that and say that is 0 because it's a circular orbit. I know that. What is the same major axis if this is 0? 10,000 kilometers. So what am I left with? Now, little omega and big omega, do they make any sense here? No, you can say they don't make any sense, or you can say I can choose to force them to be 0 degrees. It's, either way, it's fine. They don't exist. There is no line of nodes. This thing is continuously on the equatorial plane. There is no intersection between the planes. So I think in the code that you should have developed, that you are developing for your homework, you can make the choice of calling X the line of nodes, even if it doesn't exist, and call big omega 0. And the same if there is no eccentricity, you just choose little omega to be 0. There's nothing wrong with that. But really, they don't formally exist. What else is left? True anomaly. Now, see, to give me a true anomaly, then you have to choose a point from which you're counting things. And since this is circular, there's really no eccentricity line of abstraction. You know, I just put it at 0. I just count things from R0. I don't remember if these were the actual numbers, okay? I don't know if this was the example. Just look it on my website. But that's the end of the story. And so I was asking people to basically write what I told you and just reason behind that sketch and justify the numbers. And I said, if you do it this way, full credit. If you go crazy and do all the matrices and the calculations that you've done in MATLAB, it's fine, you get less credit. Because you're making it harder. And I put it there. So that kind of questions is what you should really expect. Yes?
So would you expect the entire exam to be more conceptual with no calculations?
There's a Hohmann and a bielliptic.
There was a Hohmann and a bielliptic, so maybe those...
There will be one. It's not the
Okay, so that's the calculation that you may want to do. But Hohmann and bielliptic, your book has one formula that gives you the delta V, total delta V for Hohmann and total delta V for bielliptic in one shot. So, yeah, you may want to substitute the numbers in there, but that was probably the most that they had to do.
Yeah, it's...
I don't remember if that was...
You only ask so much for a Hohmann or a bielliptic, so that should be pretty sure.
Yeah. I think we were giving, for a Hohmann transfer, radius of the first circle, radius of the second circle. And if I ask you what is the total delta V, there is actually a specific formula in the book where you plug in the two radiuses and you're done. You don't even have to do the single delta V's one by one. You have the total delta V. Remember we derived that? We looked at the different parametric plots. Yeah. So that was probably the highest point of calculations last year. So you should expect something like this. It doesn't mean that you don't have to be able to do calculations, or you can bring your calculator, but look at that test. I think that's it for today. Thank you.